Hello everyone, let's get started. So welcome to another lecture as part of our MEE 6151 Computational Heat and Fluid Flow course. So in the last lecture, we looked at the staggered grid approach, essentially to account for the pressure velocity coupling. Then we decided it should be stored as the velocity should be stored staggered to the pressure, and the x component of velocities, that is u east and u west, was stored on the east and west faces, and the y component of velocity, that is v north and v south, were stored on the north and south faces, and the pressure was stored at the cell centroids, right, the main control volumes. All right, then we also looked at the simple algorithm, the semi-implicit method for pressure linked equations, in which we noted, or we kind of created an equation for pressure correction from the continuity equation and the momentum equations, right? So we have kind of went step by step through the algorithm, and then in today's lecture we're going to continue with this algorithm. We will write the overall simple algorithm. Then we will look at under relaxation for pressure correction as well as for velocity, okay, and also we're going to discuss the several boundary conditions if you want to solve for a fluid flow problem, okay. All right, then let's move on. So coming to the simple algorithm, the first step was to guess the pressure field, right? Essentially you have to guess the velocity as well as the pressure field. So guess u star v star or ue star vn star as well as the p star, okay. So once you guess the pressure and velocity fields, you have to solve the discrete momentum equations, the discretized momentum equations, which are basically for the control volumes for u and the control volumes for v, right? These are written on control volumes that are centered around the east face, west face, north face and the south face, right, for the cell center P, okay. So then the discrete equation is given by AEUE star equals sigma NB star plus delta y times PP star minus PE star plus BE, okay. Similarly, the y momentum equation is given by A and Vn star equals sigma NB Vnb star plus delta x times PP star minus Pn star plus B north, okay. Now in doing this, we realize that of course we have guessed the pressure everywhere, and we have also guessed the u star values because these are required when we try to solve this equation. Now how do we solve this equation? You have to use either a Gauss-Seidel or a line-Bell TMA and then converge this equation to some tolerance, right? Now in doing so, essentially what we realize is that the initial guess that we had for velocities would be gone, right? By the time this equation converges, the new u star would be something that is very different from what we have guessed, but that will be the converged value. So we are not using a different variable for the converged value of u star, rather we are using the same notation. So basically once you solve this equation, the u star v star you get from these two equations is something that is converged by solving these two with a guessed pressure value of P star, okay. All right, then we also know that the A and B's that are occurring in both these equations are different because the cell control volumes themselves are different, okay. And further we also realize because we have not solved two equations together till now, what we realize is that basically these two equations are now coupled, right, essentially in some sense, because essentially you have A and B's which may contain u and v, whereas A and B's here also would contain u and v, because each of these A and B's have a d term and an f term, right, the diffusion term and the convection term. So the convection term would actually have both u and v, right, depending on the phase we are looking at. But because we have linearized the system, these values going into d and f and eventually into a and b's are known at this point, okay. So they are basically calculated based on these guess values, okay. So as a result, these are not actually, although they are coupled, you can converge for the first equation, and after that you can converge with the second equation, okay. All right, so essentially what we realized that once we converge these two equations, we obtained a converged u star and v star fields with the guessed pressure, okay. So these are obtained with the guessed pressure field, okay. Now the next step is basically is to calculate the source term coming in the pressure correction equation, that is the B term. You remember the B term on the in the pressure correction equation, that is basically the amount by which the mass conservation is not satisfied, right? So that is basically the mass imbalance that we have in the flow field. That means depending on how far these U star and V star values are from the continuity equation, this mass imbalance will drive the pressure correction equation to give the corresponding pressures, okay, the corresponding pressure corrections. All right, so the next term is to basically calculate the B term, which contains F, the mass flow rates on the west, east, south and the north faces. These are now calculated as Fe star equals rho U E star delta Y. Similarly, Fw star would be rho U W star delta Y, and F north star would be rho Vn star delta X, and F south star would be rho Vs star delta X. Now, these UE star, Vn star are basically the ones which you have got them as converged, right? Now, these are the values that will be used in calculating the star value of the mass flow rates on the faces. Okay, now that means essentially you will calculate this B term for every cell that you have in the entire domain, right? Okay, so that is what is done. After that, what we do is basically we can now discretize the pressure correction equation, that is basically AP PP prime equals sigma NBP NB prime plus B. Now you solve this to convergence, okay, because now B is computed everywhere and we know what are these A and B's and AP's, because these again depend on the delta Y by AE, delta Y by AN and so on. So those are all already known, and those AE, AN are actually the same as what we had here, okay. So they are not updated between here and here, okay. So they are the same A east, A north that we have used in the momentum equations before, okay. So and then we can solve this to convergence. Now, how do you solve this to convergence? Again, you have to use either a Gauss-Seidel or you have to use line by line TDMA and then converge this to some tolerance value, okay. So once you once you're done with step 4, essentially what you get is you get a field for your pressure correction. P prime would be known everywhere in the domain, okay. All right, then once you know the pressure corrections, of course we can now go ahead and correct the velocities and the pressures with the obtained pressure correction. So correcting the pressures is trivial. P equals P star plus P prime, that is straightforward. So you do this basically for again for every cell, and then for the velocities we have already the U star value, which is the converged value after step 2, right? Now you add U star to UE prime. Now UE prime is not directly known, but UE prime is related to P prime through D times PP prime minus P east prime, right? Basically through the simple algorithm we have related this thing. Similarly, Vn equals Vn star plus Vn prime, where Vn is equal to Dn times Pp prime minus Pn prime, okay. So basically using the pressure corrections, correct the velocities and pressures everywhere in the domain, okay. So that is basically that step is done. Now what we know is that because of this correction of UE prime and Vn prime to UE and Vn, UE star and Vn star, we get this UE and Vn field. Now this field will satisfy continuity equation because we have just solved continuity equation in a reformulated state, right? Essentially the solution for pressure correction is nothing but the solution for continuity, right? So then this field will now satisfy continuity equation. So U, east, V and P, the corrected velocities and pressures will satisfy continuity equation, but they will not satisfy momentum equations. Okay, they will not satisfy momentum equations. So this kind of requires a little bit of explanation. What do we mean by they don't satisfy momentum equation? What we mean by not satisfy momentum equation is basically that the momentum equation itself is non-linear, right? So essentially we have already linearized it. So that means they will essentially this field will satisfy the linearized equation with the original A and B's that we already had, because that's what we have done in arriving at these pressure correction equation and so on. But the u and v and p that you got would not satisfy the original momentum equation, right? The continuous momentum equation is still not satisfied by this u and v, right? So if the momentum equation were not if it were linear, let's say if the momentum equation were linear, then there is no problem, because if it were linear, then these coefficients a and b would not have had any nonlinear component which were linearized here. So as a result, this equation would be the same as the linear momentum equation, only this would be the discrete form. As a result, then this obtained u and v would also satisfy not only continuity but also momentum, okay, the continuous momentum equation. Alright, but because we have nonlinear terms, this obtained u and v and pressure fields will not satisfy the momentum equation after one iteration. However, it satisfies the continuity equation. Alright, now because we have obtained a continuity satisfying velocity field, we can now solve for any scalars that we have. For example, if you are solving for transport of, let's say, some scalar phi, or if you want to solve for temperature in your equation and so on, then you can solve for all those scalar transport equations after you have obtained the continuity satisfying velocity field. Now, why do we do it after this? Why can't we do it before? What does the resemblance what does the significance it has if u and v were not to satisfy continuity? The thing is, if you do not feed in a continuity satisfying field to the scalar transport equation, then essentially you don't get bounded solutions. So you will only get bounded solutions if your u and v satisfy continuity, right? Essentially, that means if you don't have a continuity satisfying velocity field, even if you use upwind difference schemes, you will not get bounded solution for your phi and temperatures okay. So it is very important that all the scalar transport equations are solved with a continuity satisfying velocity field, okay. So as an intermediate step, this is what we have, and we don't want to have unboundedness here, because they cannot grow more than what value that is coming in, right? So they cannot grow more than that unless there is a source or something. So that means this is important. So once we solve for all the scalars, then we know that of course we have not reached convergence yet. Then we check for convergence. Now what do we mean by checking for convergence at this stage? You check this with the original u star and v star that you started off with, right? That was basically whatever values you had guessed here. You compare that with whatever u, v you have obtained here, right? Now these will most likely be different from what you have guessed, right? And then as a result, we will not converge. So that's why basically you go to step 2 by setting, you again use the new guess values as whatever you have just obtained. Excuse me. That means your u star, vn star, ue star, vn star would be whatever ue and vn that you have got it here after correction step. Okay. So you would use that and then go back to step 2. And then again with the new pressure field, you update now a and b's, because a and b's now contain u star, v star values, which are now updated, right? With that, you would again solve for converge x momentum equation, converge y momentum equation, and then fill the right hand side, then converge the pressure correction equation, and then correct velocities and pressure, and then again solve for transport equations and so on, okay? So how many, let's say if we don't have any scalar transport equations to solve, so how many Gauss-Seidel loops do we need here? We need essentially, we need one to converge the x momentum, one to converge the y momentum, and one to converge the pressure correction, right? Either we need essentially 3 Gauss-Seidels or 3 line bell NTDMs. That is massive, isn't it? Because if you, let's say, take a cell, if you take a domain with let's say 100 by 100 cells, that means we have 10 power 4 cells. That means we have to solve Gauss-Seidel to convergence for 3 times on this 10 power 4 cells, right? Okay. Which if it is not fast might consume a good amount of time, okay? All right. Of course, if we have another scalar transport equation, then we would need to solve it here as well, right? Okay, so that is the overall algorithm. Let us make some comments on what we have learned so far, okay? So coming to the comments, the pressure correction equation that we have, AP PP prime equals sigma NBP NB prime plus B. So what this is doing is basically it is driving the velocity field, that is uv, and the pressure fields through successively continuity satisfying fields, and eventually to arrive at a velocity and a pressure field that will also satisfy momentum equations. Okay, so essentially the pressure correction equation is driving the velocities and pressures through essentially successively continuity satisfying fields, right, and eventually to obtain both continuity and momentum satisfying fields. Okay, so that's what we're doing. So essentially we are eventually reaching the velocity and a pressure field that satisfies both continuity and momentum, but we are reaching this goal or this path through successively continuity satisfying fields. So at every step, at every iteration, we have at every step in one loop of the simple algorithm, we have a velocity field that satisfies continuity. Okay, and then this will be driven to satisfy momentum through successive iterations. That means we have this outer big iteration, like this outer loop, which is basically check for convergence, go to step 2. This is basically the outer loop. Okay, so once you are done with this outer loop, then you have a velocity and a pressure field that satisfies not only continuity but also momentum. Okay, I hope that part is clear. Alright, now let us look at the kind of approximations we have made. So the corrected fields U and VP obtained in step 6, basically after the correction step, they satisfy continuity but not momentum, right? They don't satisfy the original momentum equations. And these continuity satisfying fields are used to solve for any scalar such as temperature and phi. Of course, if you don't do that, then you will not get basically bounded phi values, even if you use bounded schemes such as upwind difference scheme. Okay, even with that it will not come, because essentially your velocity itself is not continuity satisfying, right? Then you have the right hand side where you remember you had the Fe minus Fw plus F naught minus F south, that would not go to 0, and as a result you will not get boundedness for your scalars. Alright, then one of the major approximations that we made in this simple algorithm is basically after we arrived at the velocity correction equation in terms of pressure corrections. That means we wrote two such equations, one for UE prime and one for Vn prime, as A UE prime equals sigma ANB UNB prime plus delta y times PP prime minus P east prime, and the other one was A and Vn prime equals sigma ANB VNB prime plus delta x times PP prime minus P north prime, right? In doing this, what we have done is essentially we have assumed, because of the simple algorithm, we have assumed this term and this term to be 0, right? That means we have assumed these two neighboring dependency on the neighboring corrections is set to 0. Essentially what that means is that will not change the converged solution. So one question could be like, is it okay? Can you arbitrarily take this to be 0? What will happen if you don't take it to be 0? Okay, we will see what will happen. But if you take it to 0, it only says that essentially you are putting the entire burden of correcting velocity corrections on pressure corrections. Okay, because the neighboring velocities are not contributing. Okay, but we realize that this kind of an approximation will not change the final converged answer. Now why is it so? Because essentially your U prime V prime would be 0 at convergence, right? Because P prime would reach a constant value. As a result, U prime V prime would be 0. So once you have U prime V prime 0, your U equals U star. As a result, U primes are 0 everywhere. So U and B's are also, U and B primes are also 0, V and B primes are also 0. So as a result, this kind of an approximation would not change the convergent solution. It only changes the path to the solution, and more precisely it changes the convergence rate. So, but we are okay with it, because the trouble of including these terms will be much bigger than actually changing the convergence rate, because so that means this kind of an approximation only changes the convergence rate. Now what will happen, let's say if you have not neglected these guys, if you have let them be there, then what will happen? So what was the algorithm? The algorithm was to basically substitute for velocity corrections in terms of pressure corrections. Now because we could make such an approximation, we could nicely substitute for east prime as in terms of P and capital E, Vn as P and N, and similarly for west and south, and get a nice diffusion like discrete equation. Okay, But if you had, let's say, not neglected these things, what would have happened? What would have happened is basically UE prime requires not only P primes when you substitute in the continuity equations, it also requires UNB prime. Then UNB prime also would have a similar equation which will depend on its own neighbors, right? That means here it will be like AE UE prime, this is for the neighboring cell, would depend on its neighbors and some pressure corrections and so on, and then this keeps going until essentially every cell, the pressure correction for every cell will kind of be included in the equation, right? That means we are essentially talking about a global dependence, right, of solving the entire P primes in one place, which is what we don't want to do, because that would basically make it a very dense matrix, and then which we don't want to go in that direction, right? So if this is not clear, you have to kind of think about this again. Okay, that means if you had basically not taken this to be 0, then just like the equation we have written here for East prime, you will write an equation for UNB prime, right? When you go to the next cell, then A, NB, UNB prime would depend on sigma, its own neighbors, its own A and B, UNB prime, and then the pressure gradients. So that means when you go back and substitute these in the velocity correction equation, in the continuity equation, then you would get essentially not only P prime, P East prime, you will get P East prime, P East prime, and so on all the way to the boundary, right? That means it's just a big massive equation which will make it basically unmanageable to solve. Okay, so that's why we are avoiding that. That's why simple algorithm makes that these terms are 0. Now that is where the naming for simple has come. Basically it says that semi-implicit method. That is because this neighboring coefficients are basically made to 0. As a result, we are only solving for a semi-implicit. Okay, this is only implicit in pressure primes, but not a fully implicit, right? If it was fully implicit, then U prime would also depend on UNB primes. Okay, so in order to save computational effort, we are doing that, and that's where the naming for the algorithm as semi-implicit comes into play here. Okay. Okay, and the remaining part, the pressure linked equations, is basically we have the current momentum equations are linked to the pressure. Okay, that's what the naming comes from. Okay, all right, then essentially if we continue to look at this neglecting the neighboring coefficients, then basically your AUU prime has two components. One is sigma NB NB prime plus delta y times PP prime minus P East prime. Similarly, A and Vn prime equals sigma NB Vnb prime plus delta x times PP prime minus Pn prime. That means there are two components. One is the velocity correction. Here depends on neighboring velocity corrections and on the pressure corrections. So we are taking the neighboring velocity corrections to be 0. That means what we're doing is, by doing so, the velocity correction at a particular phase has to be completely done by the pressure corrections alone, right? Because the neighbors do not contribute. As a result, the delta P prime values that you would get would be quite large. Okay, that means having larger values for this P prime, PE prime would lead to poor convergence rates. Okay, this will lead to poor convergence rates. As a result, the P prime equation that you have, the pressure correction equation, will not converge very quickly. Okay, it will kind of be very sluggish. So as a result, we have to kind of under relax the pressure that we get. Otherwise, this will become like very large values. So one way to under relax is basically the pressure equation is P equals, when you correct the pressure, you add only a portion of whatever P prime that you got out of the pressure correction equation. That means you write P equals P star plus alpha P. This is some under relaxation factor. It could be 0.2, 0.3 depending on the situation, or 0.8 times P prime is what you do. And the non-linearity of the momentum equations also calls for under relaxing the velocity corrections, okay, because of the non-linearity. But we will not under relax it in this way, okay, in the way we have done the pressure under relaxation, because let's say you will not write UE equals UE star plus alpha U times UE prime and Vn equals Vn star plus alpha V times Vn prime. You will not do this, because if you do it this way, essentially the velocities you are getting after correction will not satisfy continuity. Okay, so essentially this this will not be satisfied. Okay, the continuity, this will not be satisfied. So do not underlax basically this way. Okay, so do not underlax them this way. We will see how to underlax the velocities using our original way. Okay, that means using the momentum equations itself. Okay, because if you do this, if you modify, then your UE, UW, V north, V south that you get would not make it to 0, right? You will get a velocity field that will not satisfy continuity, because F east minus FW plus F north minus F south would not be equal to 0, right? So entire purpose would be gone. So as a result, the nonlinearity in the convection term of the momentum equations also calls for under-relaxation, and we underlax the momentum equations in the following way, essentially in the original way that we have discussed. So if you have the discrete momentum equation as AEUE equals sigma NB1B plus delta Y times PP minus P east plus BE, then of course, how do you underlax this thing? Basically, you add and subtract AEUE star, and then you multiply the component with some alpha u. Okay, then if you rearrange, then what you get is you get this coefficient IAE going up by divided by alpha u times UE equals sigma NB1B plus delta Y times PP minus PE plus BE, plus you have this extra term, right, which is 1 minus alpha u by alpha u times AEUE star. Now again at convergence, UE star equals UE. As a result, this 1 by alpha u times AEUE star would get cancelled with this term, and then your alpha u and alpha u get cancelled here, and what you get is AEUE star with a minus that can be taken back to the left hand side, and you get the original equation here. Okay, this we already have discussed in the context of under relaxing the equations, right? This part we have already discussed. So we can do a similar thing for the Y momentum equation, that is AN VN equals sigma NB UNB VNB plus delta x times PP minus PN plus BN. And if you want to underlax this equation, you write basically AN alpha V times VN equals sigma NB VNB plus delta x times PP minus PN plus BN, plus you have 1 minus alpha V by alpha V times AN VN star. So one question could be again, what would be the values of alpha u and alpha v? Again, they are dependent on the case. You could probably take them around like 0.8 or 0.7, and they need not be the same. Okay, they can be different as well, and they need not be same as the pressure under relaxation as well. Okay, all right. Now let us look at couple of things. That is basically, before we go on to the boundary conditions, we will look at the relative nature of the pressure in incompressible flows. In this also we will kind of invoke a little bit about the boundary condition, and thereafter we will look at the complete set of boundary conditions that we can apply in the solution of fluid flow equations. Okay, so in the context of incompressible flows, we say that the pressure has got a relative nature. That means what we say is that the absolute value of pressure does not matter, because it doesn't feature in the equations, right? It's the gradient of pressure that is featured in the equations, in the governing equations, which are basically del dot u bar equal to 0. Essentially, if you're talking about a steady incompressible flow, your continuity equation is del dot u bar equal to 0, and your momentum equations are del dot rho u bar u equals del dot mu grad u plus su minus I dot grad p, and the Y momentum equation is del dot rho u bar v equals del dot mu grad v minus j dot grad p plus sv, right? Essentially, it's only the gradient of pressure that matters. So because you don't have an equation of state or something that can control the absolute, that can introduce the absolute value of pressure into the system, so as a result it's only the gradient that matters. But okay, that is fine when we state it theoretically. Let us see why we say that the gradient is the one that matters, not the absolute value, by using a couple of examples and also through some analyzing some of the boundary conditions. Okay, so let us take basically an example here. This, on the left hand side you see basically a cavity. Let's call this as a square cavity. In the literature this is known as lid driven cavity flow. Essentially, let's say we have a box like this, on which the top of this box is, you could think of this as a belt or something that continuously moves. Okay, in the positive x direction. So there is a belt that is moving, and then it kind of comes back, and essentially it has a lid on the top which kind of moves continuously in the x direction with a velocity of let's say 1 meter per second. So u bar for the lid is 1 I cap plus 0 j. Okay, whereas the all three other boundaries of this box are stationary, so they are not moving, so their velocity is 0 on all the three sides, and this box is filled with, let's say, water. Okay, so it's filled with water, and then if the belt is moving at a certain speed, then after let's say a particular steady state is reached, then you will see that the water inside, the fluid inside the cavity also starts rotating because of the belt. Okay, and these are some of the streamlines. Of course, these are only a representative because they are not drawn continuously, and we know that streamlines cannot end like this somewhere in the middle of the flow abruptly. Okay, these are only kind of indicating the direction. So we have some kind of flow that is set up. Now what we see here is that what are the boundary conditions that we have specified in solving this problem. The only boundary conditions we have specified are basically for velocity, right? Essentially velocity is 0 here, and velocity is 0 here as well, and 0, and it is 1 I cap on this top lid, where we have not specified pressure anywhere. Okay, so we have not specified pressure anywhere. So what consequences does it have in the solution of fluid flow equations, or even in the solution that is obtained here? Okay, so to do that, let us look at one of the cells that is sitting right next to the right hand side boundary here. So we are talking about, this is the right hand side wall, and if we have, let's say, a staggered velocity representation, basically u east on the faces, u west on the west face, v north, v south, and p cell, and we don't have essentially this east cell at all, right? This is not there, this is only shown for representation. So you have P and W cells, and this is the primary cell. Okay, all right. That means what happens now? What will happen to the P prime equation when you try to solve for this near boundary cell? Okay, essentially for the near boundary cell, what will happen to the P prime equation? Okay, that means your UE is UE star plus UE prime, right? That's what we would use in obtaining the P prime equation, but we know that UE is already specified, right? So UE UE value is specified, so we cannot correct it. Okay, so we cannot write UE equals UE star plus UE prime, so leave UE as it is. So this is a known value. That means once you know, that means velocity correction on this, for this particular phase, would be 0. UE prime is 0 on this particular phase, in fact for all the phases that share this boundary. In fact, if you look at this problem, UE prime would be 0 for all the cells here that share near this boundary, and here all the V south prime would be 0. Similarly, UW prime would be 0 here, and V north prime would be 0 for all the cells that share, that are adjacent to this top boundary. Okay, that's what we are saying. That means we already know what is the value, then we should not write it in terms of star and the correction values. Okay, all right. Then if you look at the starting point for the pressure correction equation, we are starting off with the conservation of mass, right? Essentially Fe minus Fw plus F north minus F south equal to 0. This is the continuity equation, and because these are now used together with U east, U west, and so on, these will satisfy continuity. If there were stars on this, these would not satisfy continuity, right? If there were stars here, this will be not equal to 0. Because there are no stars here, this is equal to 0. Now this Fe value is already known. Of course, in this particular context, if UE is 0, Fe is 0. But in general, let us say Fe equals rho UE delta y. This is already known. So let us substitute for this guy. Once that this is known, where will this term go? This term will go into the B term, right? Okay. That means we can write this as, and the remaining terms, that is F naught, Fw, F north, and F south, can be decomposed into star values and prime values, leaving Fe as it is. So Fe minus Fw star plus Fw prime plus F north star plus F north prime minus F south star plus F south prime equal to 0. Okay. Then we can rearrange this by sending the star values to the right hand side and also the Fe to the right hand side. Okay. That means the B term now contains Fw star minus Fe minus F naught star plus F south star. Again, if fe happens to be 0 because of something, let it be 0, but otherwise this is the formulation, right? And on the left hand side now we are left with only 3 terms that correspond to the primes of the flow rates. Those are minus Fw prime plus F naught prime minus F south prime, okay, and for which we can now substitute in terms of the velocity corrections, in terms of uw prime, and uw prime can be again written in terms of pw prime and p prime, and we have this particular equation, right? Basically minus rho dw delta y times pw prime minus pp prime plus it's basically rho dn delta x times pp prime minus p naught prime minus rho ds delta x times ps prime minus pp prime equals b, okay? All right, that means we see that there is no p east prime. That means there is no connection to the p east prime, right? Of course, that makes sense, it should not be there. What about, that means what about AE? That means AE equals 0 because there is no contribution to of that term to either to PW or either to P east or to PP, right? So AE equal to 0. That means we only have 3 neighbors, and the contribution to AP will only come from west, north and south, okay? It will only come from north, west and south. Let us say if you have this kind of boundary condition that is specified on all the boundaries, right? On all the boundaries velocity is only specified, then what will be the consequence of P prime equation? Let's say similar to this, what will happen? Then AP prime equals, AP PP prime equals sigma NB PNB prime plus B, and would it satisfy Scarborough criteria? Because A east equal to 0, that means AP would be only a summation of AW, A north and A south, right? So it would satisfy, it will satisfy Scarborough criteria, but it will only satisfy in equality, okay? Because for this particular problem, every cell behaves like this. That means everywhere, all the boundaries, it will only satisfy in equality, right? Because the corresponding coefficients will be different, but that means all the cells, including the bounded cells, will only satisfy in equality. That means it will never satisfy in inequality. But then, okay, then how do I solve for this problem? Will it work? Yes, it will still work, because Scarborough is only a sufficient condition, right? So you will still be able to solve for this. In case if you cannot solve for this, then use under relaxation here, right? Essentially bump up the AP value by dividing it by some under relaxation, and then it will kind of converge. But what we see is that because of this Scarborough only satisfied in equality, we see that both P prime as well as P prime plus C will be solutions, right? Because now AP equals sigma NB, so whatever P prime you get, if you add, so whatever P prime equation that you got in terms of your XY distribution, this will satisfy the equation that you get here. Not only that, your P prime XY, if you add a constant value of something, that will also satisfy your pressure correction equation, okay? So that means when you don't have a boundary condition for pressure, right? When you specify all velocity boundary conditions, then you can only determine pressure up to a constant, right? Right? You cannot specify. You cannot get pressure to absolute value, right? You can only specify. You will only get pressure up to a constant, right? All right. Then how does the iterative solvers and direct solvers behave? So if you are using an iterative solver like Gauss-Seidel, then this will converge. Otherwise, you have to use some kind of an under relaxation. And what will be the consequence for a direct solver? If you have a direct solver, what it means is basically when you have all velocity boundary conditions, you have essentially what we're talking about is we're talking about a rank deficient system, right? Because you have these continuity equations, and one of the cells, the last cell that you have, let's say if you keep writing the continuity equation, the last cell would not be contributing anything new. As a result, one of the cells, the equation for one of the cells can be written as a linear combination of the equations for using all other cells, okay? So as a result, direct solver will not work in this context when you have all velocity boundary conditions. So one fix for this is basically you have to set pressure or pressure correction equal to some fixed value for one of the cells, okay, and then don't solve for the cell and then solve for everybody else, okay. That means what we're talking about is that if you have all velocities specified, the absolute value of P doesn't matter in incompressible flows. It's only the pressure gradient, because whatever pressure you get, if you add another constant to that, that will also satisfy the equation, pressure correction equation, also as the momentum equations as well, okay. As a result, your P doesn't matter in incompressible flows, okay. It's only the pressure gradient that matters. All right, now let us take some examples and see why we say that the pressure gradient only matters. If you have, let's say, consider a channel flow. So basically we have two walls, one on the top, one on the bottom. The flow is coming from the left. We have an inflow and we have an outflow, and what we specify is we specify pressure here, okay. Let's say we are now talking about a different problem, and we are not talking about velocity boundary conditions. We are talking about pressure boundary conditions, both at the inflow and at the outflow. Now if this pressure at the inflow is higher than the pressure at outflow, of course the flow will go from left to right. And in case 1, we maintain a uniform pressure of 100 kilopascals at the inlet, and at the outlet we maintain a uniform pressure of 50 kilopascals, okay. That means and then we can solve for this system, okay, and obtain, let's say, using simple algorithm, and then obtain what is the velocity and the velocity field, okay, for this. Now in the second case, we change the inflow pressure to 300 kilopascals and the outflow pressure to 250 kilopascals, okay, and again solve for the velocity field here, and they obtain another solution u and v for the entire domain here. Now would this velocity field that you have obtained be different from this velocity field that is obtained? Would uv obtained through the case 1 be different from uv obtained from 2 or not? What would be the thought process here? Would they be the same? The pressures are different. Basically in the first case we have 100 and 50, and here we have 300 and 250. But still the velocity field that you calculate using the solution or in an experiment would be the same, right? The uv that you get from both systems would be the same, because it's only the pressure gradient that matters, right? It's only the pressure gradient that matters, because you have 50 kilopascals from inlet to outlet over a certain length L here, and same pressure loss here as well, and that is what matters. So the pressure gradient only matters. As a result, the absolute value of the pressure at the inlet or outlet doesn't matter. As long as you have the same pressure difference over the same length, then you will get the same velocity field, okay. That is something to know about, which is also same as what we have discussed before in the previous problem. Now what about if you take another case where instead of having both pressure inlet and pressure outlet, we maintain pressure outlet, whereas we maintain a velocity inlet. So we provide V bar or U bar at inflow, and we provide a pressure at the outflow. So in the case 1, we provide 5 meters per second as velocity at the inlet, and we maintain a pressure of 100 kilopascals at the outlet. And in the case 2, we keep the same velocity, that is 5 meters per second, but we change the pressure to a very small value. We just make it 10 kilopascals. Then you obtain, let's say, velocity and pressure field using simple algorithm, and then here also you solve using velocity and pressure field everywhere, and compare this field with this field. Now would u and v obtained through case 1 be different from u and v obtained for case 2? Would they be the same or different? They should be the same, because we have maintained the same inflow. Although the pressure is different, the pressure at the inflow would come out to be this pressure plus this gradient times this length, okay. So that pressure gradient will still be there, will come out through your algorithm, and essentially your P inflow will be different. That means P1 and P2 would give a different pressure field here, okay. But the pressure gradient would be the same for both cases, and the velocity fields that you get from the case 1 and case 2 would come out to be the same, okay. But your algorithm will tune itself to get accordingly a pressure here, which will be this outflow pressure plus the gradients times this length, okay. So as a result, you will get the corresponding pressure field here, which will be of course different from here, but the pressure gradients will be the same, and the velocities will be the same. The velocity vectors, magnitudes, everything will be the same here, okay, between the two cases. All right. So that kind of emphasizes the role of pressure only as a relative nature, essentially, because the gradient is only matters, the absolute value of pressure doesn't matter. Okay. All right, now let us look at the final component of this today's lecture, that is basically the boundary conditions, out of which we have already seen how to tackle the velocity boundary condition. So we will look at other boundary condition, that is the boundary condition for pressure as well. So if you look at the equation, we have the continuity equation, that is del dot u bar equal to 0, and then the x and the y momentum equation, that is basically del dot rho u bar u equals del dot mu grad u plus, okay, this term is supposed to be actually minus I dot grad p plus su. This is the discrete part, so this, don't worry about these two. Basically, and then we have for the y momentum equation, what we have is del dot rho u bar v equals del dot mu grad v plus minus j dot grad p plus sv. Okay, these are both are basically similar to the general scalar transport equation. So as such, we know how to handle the boundary conditions for these convection and diffusion terms. Okay, it's only basically a matter of changing phi to either u or v and solving them, right, for Cartesian meshes or for orthogonal meshes. In fact, we also know how to do this for non-orthogonal meshes. Okay, so there is only one extra equation that was introduced in the simple algorithm, and that is basically your pressure correction equation, right? This is the only one that was introduced in the simple algorithm, that is the pressure correction equation. So we need to see now how do we handle the pressure correction boundary conditions in the pressure correction equation is something that we have to look at, because everything else is already known to us. Okay, how does the pressure correction equation behave if there is a velocity boundary condition? This thing we have just already seen, so that means, let's say we will kind of look at it again. So that means if we have an inflow, and this is a cell that is adjacent to the inflow, where UB bar is specified, let's say this west face is nothing but B, and this P cell has east face, north face and south face. Of course, there is an east cell here, north cell here and south cell here, which are not shown here. And if you write the conservation of mass for this particular cell, that means what we get is F east, the mass flow for the east face, minus FB, that is for the west face, plus the mass flow rate for the north face and the south face equal to 0, right? And we know that FB is basically your rho u b delta y, that is already known, right? Essentially, this value is already known. Okay, this is already known because UB is known and everything else is known. Okay, that means what we do is we will not substitute FB in terms of FB star and FB prime. Okay, we will just leave FB as it is, and we will write other components FE star, FE, Fn, F south in terms of star and the prime values. So the equation we get is Fe star plus Fe prime minus Fb plus Fn star plus Fn prime minus Fs star minus F prime, Fs prime equal to 0. So the discrete pressure correction equation now becomes APPP prime equals sigma NB PNB prime plus B. So your A east, which is rho d delta y, and there is no AW because we don't have any terms coming from there. A north equals rho dn delta x, A south equals rho ds delta x, and your AP would be summation of only east, north and south because there is no west coming into play, and B equals your FB, that is the known value, minus Fe star minus Fn star plus Fs star. Okay, that means what we have got is basically an equation which is in terms of north, south and east, and the B values have gone into the right hand side. Okay, now does it satisfy Scarborough criteria? Yes, it does, but it only satisfies in equality because AP equals a sigma A and B only. So that means in the absence of source terms also it only equals this thing. That means both because of this property AP equals sigma A and B, at convergence both P prime, at convergence B goes to 0, that means both P prime and P prime plus constant are both functions. As a result, the pressure can only be found up to a constant, right? Essentially the pressure level could not be determined, only up to a constant, so we cannot determine the pressure level, but the pressure gradient can be found. But if there is a P reference, pressure reference, then the entire pressure can be found or expressed relative to P reference. Okay, that can be done in case if you have all velocity boundary conditions. Okay, like in the case of the lid driven cavity problem. Okay, this we have already seen. What about the pressure boundary condition? So the other boundary condition you can get is a pressure boundary condition. Then you can specify some value for the pressure. That means P. Let's say we are talking about an outflow. This is a cell that is adjacent to the outflow. So we have the P cell, we have east, west, north, south, and B is now the boundary phase, and the pressure on the boundary phase is constant. Okay, this is specified. That means we are, let's say the channel is flowing out into some atmospheric pressure. Because PB basically is specified, the pressure is fixed, so there is no correction. That means PB prime, which is also equal to PE prime, equal to 0. So there is no correction required for the phase value of east for pressure. Okay, that means PB prime equal to 0. Then what happens to the discrete pressure correction equation? We have AP PP prime equals sigma NBP NB prime plus B. Now if you look at the equation, what happens is basically you will get in the equation for velocity correction for the phase east, okay, what will happen is AUE prime equals delta y times PP prime minus PB prime, right? PP prime minus PB prime is what you will get for AE prime, okay, but we know that the PB prime is 0, right? This value is 0, okay. That means UE prime also equal to UB prime is delta y by AE times PP prime, okay. That means this contribution of DE is only going into the AP but not into A east, okay. As a result, A east is 0, right? A east is not there, it's only going into AP, okay. That means but we know that what is that means if you write the entire system, what you get is essentially there is no A east, okay. So this A east is basically AB. AB equals rho dB delta y, which we got it from here, okay. Basically once you know what is UB prime, your FB prime is rho UB prime delta y, so rho dB delta y, this becomes AB, right, which is basically written here, rho dB delta y times PP prime. So there will be a contribution going into AP prime or PP prime coefficient, that is AP, but not to A east, okay. That means AP would again be summation of A west, A north and A south and AB, right, AB, but A east itself is 0, okay. So we can say A east is 0, but AB term will go into AP, okay, for pressure boundary conditions. So you may need to derive this yourself, okay, once again. So one thing that you would see which is different here is because you have only pressure gradient, you don't get that half delta x terms here, because this delta y corresponds to area. As a result, you don't have that half. You remember for the diffusion we had that delta x by 2, delta y by 2 coming, that won't be there, because now we are talking about gradient theorem applying to grad P. You will only get P east minus P something minus P something here. That would be PP minus PB, okay, and PB itself is 0, PB prime is 0 because of the pressure boundary condition. Only this term survives, okay. That means in the original equation, the pressure correction equation for this particular cell, what we get is AB PP prime equals sigma NBP NB prime plus B, where the neighbors are only the capital W, capital North and capital South, West, North and South, and A West, A North, A South are the same as before, that is rho dW delta y, rho d North delta x and rho d South delta x, and AP would be equal to A West plus A North plus A South plus AB, okay. And your B term now has minus FB star plus FW star minus F North star plus F South star. Basically this is nothing but my rho minus FE star. And how do you get F east minus F east star? This comes from the momentum equation for the cell, right? We know how to discretize the momentum equation, and from there you will get what is F east star here, okay? That we will substitute. So what about Scarborough criteria now for this particular problem if you have a pressure boundary condition? So Scarborough is it satisfied? Yes, it is satisfied. Is it satisfied in equality or inequality? Inequality, because AP is now greater than its neighbors by AB. Okay, so essentially Scarborough is satisfied in inequality. That is a good news, because then our iterative solvers will have no problem. And what about convergence? At convergence, would both P prime and P prime plus C would be solutions? No, because AP is not equal to sigma NB. This will always have this AB effect, right? As a result, only P prime is the solution, right? So basically, when you have pressure boundary condition, P prime plus C will not satisfy the pressure correction equation. Okay, it's only the P prime that you get. As a result, now the pressure level is fixed, because through the boundary condition that is given, the pressure level is now fixed, right? That means you cannot have any arbitrary pressure values inside the domain. They are all expressed relative to the pressure boundary condition that is given. Okay, so pressure, but still it is only the relative pressure that matters. Okay, that is not any different. Okay, so that is how essentially we apply boundary conditions for pressure and velocity when it comes to the pressure correction equation in the solution of the incompressible flow equations using simple algorithm. Okay, so what I'm going to do is I'm going to stop here, and in the next lecture we're going to solve some problems, exercise problems from Patankar's book. Okay, so I will try to post these problems, and then we can first solve them by hand, set up the algorithm, then we can go back and look at the code and see how to run them and get the solution and stuff like that. Okay, I'm going to stop here. If you have any questions, write back to me through email. I will respond back. Okay, thank you. Talk to you in the next lecture.